to introduce JUICE with a forward before we get on to our two main speakers, I'd like to hand you over to Claire.
Okay, so yes, this is just a brief introduction to give you a status on JUICE. So JUICE is doing very well. Actually, yesterday we were celebrating the third launch anniversary with our colleague from the Mission Operations Center in Darmstadt, because now JUICE is already well inside its cruise phase. We had actually an excellent cake prepared by our spacecraft operations manager that is not only a very competent spacecraft operations manager, but also a very good cook. So you can see here, you can recognize JUICE, of course, and with a little bit of artistic view, you can also see Atlas, Comet Atlas and the Sun, but this will be much more details and with much more precise details by the two upcoming speakers. So just a quick view on, a bit annoying this, yes. So just a quick view on the cruise phase. So we probably already showed these plots to you before. This is the, let's say, the path for JUICE to arrive to Jupiter, its main target. So you can see as a function of time, the distance to both the Sun in orange and the Earth in blue. And the background indicates specific portion of the trajectory where we are either close or very close to the Sun and where we have a more stringent thermal constraint in particular. So as of today, we have done already 36% of the cruise. We have been for a long time in the inner solar system. We have performed already 2 gravity assists. The first one was the Lunar Earth gravity assist. There's a specific Europlanet webinar on this and on the outcome of this double gravity assist. We had the Venus flybys in August last year, and we are now in the colder place in the colder cruise phase. The next in line will be then the second Earth flyby that will happen in September this year. So the teams are the operations teams are very busy preparing for these flybys, and you can see that not only we have cake, but we had also cookies yesterday to illustrate the next JUICE target. But this is what we were expecting to have during cruise phase. What we didn't expect, and which is the topic of today, is of course our visitor from interstellar space, so 3I Atlas. So in July, the comet was first detected in Chile, and very quickly it appeared that JUICE was in a very, very good position, while Atlas was actually getting very close to the Sun. While also the Earth was in conjunction with the Sun, so with a very limited possibility to actually monitor the comet from ground-based. So with the help of the operations team and of all the instrument teams, or at least the one that participate to this campaign, we set up altogether a campaign in November 2025, where 5 of the JUICE instruments operate, 5 plus the navigation camera, and you will hear more about this by Tobias. So basically, this was quite a challenging activities. First, because we were not supposed to operate the payload at this point. This was also the time where we were just exiting the very hot cruise, what we call the very hot cruise, where we have very stringent, as I was saying, constraints in terms of thermal. We have a very limited capability to off-point the spacecraft. We use, during those hot cruise, we use the Huygens antenna as a sun shield. So basically we point the Huygens antenna to Sun continuously. And we have only a very limited possibility to off-point. So looking at Atlas was also quite a challenge during this period. And in addition, we had a very low bitrate capacity at the time. So that means that we had to wait, although the campaign took place in November, we had to wait until mid-February until we were able to actually get all the data on ground. So that's why we are having this webinar now, because the teams have been receiving their data not such a long time ago, and they have been looking at it quite intensively in the past weeks. So with that, I think I will give the floor to Elena that will actually show some very interesting data that we got from the JANUS scientific camera.
Thanks, Claire. Just while you're doing your slides, Elena, allow me to introduce our next speaker. Elena is a researcher at the INAF Astronomical Observatory of Rome. She's a solar system scientist working on small solar system bodies, mostly on solid component of comets. Previously co-eye of the JADA instrument on board Rosetta, she's presently a member of the Target Identification Working Group for the ESA mission Comet Interceptor and co-eye of the JANUS instrument on board JUICE. Welcome, Elena.
Thank you, Callum. Thank you to everybody. Let me share my screen. Thank you to everybody for being here. In this part of presentation, I will show some of the first results that, as Claire had pointed out, we are obtaining in these days and weeks, because we are working on the huge data set, fortunately huge data set that the JANUS camera on board JUICE was able to obtain during the observational campaign at the 3I Atlas interstellar comets in past November. Here is, okay, let me see, okay. It's just a very brief outline of what I will talk about, because I will very briefly introduce to this new page of cometary science that actually started less than 10 years ago, with the discovery of the first interstellar object inside our own solar system. Then I will briefly discuss what we in the sense of the cometary community was able to obtain during the intense observing campaign that was performed on 3I Atlas during its inbound orbital branch. And then we will go through the first results, the first, in my opinion, I hope also that will be also your opinion, beautiful images coming from the observations of by JANUS. So, as I said, it is a quite young page of the cometary science. Of course, models of formation and evolution of solar system made us expect this target to be somehow present in the interstellar space. The Oort cloud that is in the far and coldest part of our solar system sometimes is dynamically perturbed, and a number of comets are injected inward our solar system, and they became visible almost every day, but many of these targets are ejected outside our solar system. So applying the same model of formation and evolution and behavior of a planetary system, there is a number of these interstellar objects that move from one planetary system to the other. And up to less than 10 years ago, in fall 2017, the first of these interstellar visitors coming from other suns became visible inside our solar system. It was 1I Oumuamua, which was discovered by the Hawaiian telescopes, and in fact Oumuamua is an Hawaiian word which means messenger coming first from very, very far away, and it was identified at first as an interstellar asteroid because no cometary activity was detected. It was actually detected during the few observations that were possible during its passage inside our solar system, because it was discovered when it was around less than 10 the 2 AU, and left us a few weeks to observe and study its characteristics. Colors and light curve that were obtained depicted a scenario of strange object, rather small, reddish, irregular, and rapidly tumbling, which colors resembled some small asteroids that moves inside our solar system. Less than 2 years later, in summer 2019, Gennady Borisov, with its own self-constructed telescope, discovered the second member of this still scarcely populated family of interstellar objects, which was immediately identified as a comet. To I. Borisov immediately showed a typical cometary coma. It was discovered when it was at 3 AU along its inbound orbital branch. It showed a well-structured coma and tail, and its color and its composition resulted quite similar to many of the comets that move inside our solar system, more similar to short period comets than long period comets coming from our Oort cloud. The picture changed last summer. As Claire pointed out, in July 2025, the third of these interstellar objects, 3I Atlas, was discovered, and one was discovered on its inbound orbital branch when it was rather far from the Sun, at around 4.5 AU, and was already a coma, a well-defined coma, and was immediately identified as a comet. And given the distance and the fact that almost all its inbound orbital branch would have been accessible to telescopes, 3I Atlas became the target of a huge observational campaign with ground-based telescope, but also with space telescope and also with instruments on board mission that were not planetary or cometary at all. Its velocity, its direction, its motion inside the solar system immediately depicted the scenario of an unusual object, unusual target, even if the precise history of its evolution, just a moment. Okay. The history of its path through the galaxy is not perfectly assessed. It is maybe quite ancient, maybe more ancient, older than our own planetary system, and the amount of information that the science community gathered on this target allowed to, or is still allowing to depict particular scenarios and ideas of its origin. And we will see in a moment which is the most the idea that is now discussed inside the community. As I said, 3I Atlas was the target of an intense observational campaign. I collected in few slides some of the information that were available before the JUICE observations. It was observed with the space telescope like Hubble Space Telescope in the left panels, or the infrared JWST telescope in the middle panel, showing, as I said, a well-defined coma and incipient tails since the beginning of its inbound orbital branch, known inbound orbital branch inside our solar system. It depicted colors similar to those observed in our in small bodies, in comets moving inside our solar system, even if it showed reddish coma colors with respect to long period comets pertaining to our solar system. Also, its composition was explored with space telescopes like JWST, and with, as I said, also mission like Spherix that is operative since March last year, and it is not a planetary mission, but it was immediately involved in this campaign in order to characterize this very peculiar object. The scenario is that of a CO2 dominated coma, of an hyperactive comet with the possibility to different sources of the gas amount inside the coma. Maybe the same mechanism that has been invoked for a short period comet like Hartley 2, the presence of icy grains inside the coma, which contribute with sublimation of their surface ice to the total amount of gas measured inside the coma itself. Approaching perihelion that occurred at the end of October 2025 at an heliocentric distance of around 1.4 AU. The outgassing, of course, increased, and many other species were detected from ground-based telescope, like, for example, the Telescopio Nazionale Galileo or the Keck telescope. These are only the very few spectra that has been obtained during the intense observational campaign that has been performed, that allowed to derive the presence of the CN inside the coma, giving the characteristic green color of the coma itself, or also some faint lines attributed to rare compounds, like, for example, the nickel, or that has been observed in other comet of our solar system, but not at this large heliocentric distance. So the issues is still on debate inside the community. And also it has been detected a high water production rate with some specific characteristic of the isotopic composition of the comet. All of these results allowed to define very peculiar definition of this comet given by Professor Bodewis, because 3I Atlas has been defined as an extreme comet, but not an exotic comet. The same species that have been measured in the years in solar system comets, both in short period and long period comets, have been observed in 3I Atlas, but with different relative abundances. The isotopic composition, for example, the water that is very enriched in deuterium, or C12, C13 ratios for 3I Atlas are unusually with respect to previously observed comets. All these analysis underline the fact that the 3I Atlas could be considered a preserved fragment of a planetary system rather different from our own, which maybe is formed in a different part of our galaxy, and 3I Atlas itself may be formed in a cold and distant place with respect to her sun or his sun. No. And this enhances the importance of this peculiar object, of these new objects that moves inside our solar system, and is one of the goal of the next comet mission of ESA, which is Comet Interceptor, which will be dedicated to the exploration of a long period comet, possibly moving for the first time inside our solar system, but its goal is, of course, to perform a detailed in situ characterization of an interstellar comet, should an interstellar comet become visible during the putative operative phase of the mission itself. So, unfortunately, all these results that were gathered during the inbound orbital branch were not possible to continue. The exploration was stopped just before the perihelion, because just at perihelion, when the solar radiation is at its maximum, the comet was not easily observable by ground-based telescope. The perihelion passage was on the other side of the sun, but like as Claire pointed out, immediately was clear that many instruments, and in particular many spacecraft, and including JUICE, would have been able to target 3I Atlas during the perihelion, or at least just after the perihelion. And in fact, planning this observation was not simple, also because the 3I Atlas and JUICE relative movement is very tricky. The comet moved very, very quickly, not only with respect to the solar system, but also with respect to JUICE, and the framework was rapidly changing. So it was quite difficult, or at least very demanding and challenging, to program the observational campaign. And it was a difficult period because JUICE was coming out from the hot phase. So it was very tricky, as Claire pointed out. But nevertheless, the ESA team took the opportunity to point the comet and to let many instruments on board work and try to obtain something that they were not designed for, because it should be reminded that all the instruments that are on board JUICE are being designed, the constraints and the performance have been tailored for their main aims, in particular for the JANUS camera. This is the scientific camera that is on board JUICE. Its main aim are to characterize Ganymede, Callisto, and Europa as planetary bodies, and to perform characterization of the ring system, possibly investigate Jupiter, the irregular and inner satellites of the planet. So it is not a camera that has been designed for cometary science. And here are some of the characteristics of the instrument. PI is Pasquale Palumbo, PI Ania Portianchina, and it is a small telescope, as you can see. It is equipped with a filter wheel that has 13 filters that cover the wavelength range from 340 to 1080 nanometers, so from the near UV to the near infrared. And also the filters have been selected for the foreseen operative phase at the Jupiter system. Nevertheless, many of these filters have been considered very useful to perform an observational campaign on the 3I Atlas comet. And here are some details on the campaign. The observational campaign was organized in 5 observing slots from November the 5th to November the 25th. With the comet moving from an heliocentric distance of 1.38, so just few days after its perihelion passage, through to 1.7 AU. The spacecraft moved very quickly, moving away from the comet during the campaign, and more than 120 images were obtained using 7 filters distributed along the slots, allowing a complete spectral coverage from the near UV to the near infrared. And the images were collected with different exposure time. Particular sequences of images with increasing exposure times were programmed in order from on one side to enhance the external and expected faintest isophores of the coma, and on the other side to obtain images, not saturated images, in the central condensation where the nucleus is expected to be. And so the filters were selected from a panchromatic filter in order to obtain, let's say, visual images of the comet to narrow band images in the blue, red, and green region of the spectrum, and then also in the near ultraviolet and in the near infrared part of the spectrum. So let's go to some of the results, which I share with you. These are some examples of the images of the campaign performed in the F1 filter, which is the panchromatic one. This is an image of around 30 seconds of exposure, full frame. This is the frame, the projected field of view of the JANUS camera, with the linear size that you see there in the table, and obtained in November the 5th. So this is the closest images that we have in the panchromatic filter, with a visualization enhancement in order to see the complex structure of the coma that we will analyze in more details in a few moments. Then, when the comet moves away from the sun and the spacecraft moves away from the comet, the images became this one. This is an image obtained in the second slot at around November the 12th. Then again, the comet moves away from the sun, the spacecraft moves away from the comet, and this is an image also in the panchromatic filter obtained on November the 19th. And this is one of the image of the last slot obtained on November the 25th, where the structure of the comet appears quite faint with respect to the star field, the background star field. So this is the complete, this is an example of image sequence in the pan filter for all the slots, 5, 6, 12, 19, and 25 of November. The distance of Juice varied from slightly more than 60 million kilometers to slightly less than 190 million kilometers. And the aspect of the coma, in particular in the first 3 slots, appears quite interesting in the panchromatic filter when considering the complicated geometry of the view of Juice. I superimposed here the vectors representing the directions, and you will see that if we imagine that we are Janus and we are looking at the comet, the sun is on our back. So we are looking at the comet with the sun on our back, and so the tails, the structures that we see are heavily projected on a 2D sides in the full field of view. So all this complicated geometry should be taken into account when we make any consideration about the structure that we see. In the panchromatic images sequence that we show here, the coma and the tail structures are due to the combination of all the components of the coma, the gas and plasma tail, the dust of different size. And for the first 3 slots, the length of the antisolar gas tail, here we see heavily projected in a 2D view, is limited by the edge of the fields. And considering the geometry and the sun position in the observing time, the tail is larger than 4 and more than 2 million kilometers on given observation times. If we consider the let's say the color filters, the framework is even more interesting. In this animation, we show the transition between the near ultraviolet, the blue one, and the near, or is this the red one, the red image. So for the first slot, November the 5th. So you see how the general aspect of the coma changes when considering these different filters, and so the different component to the comet signal. And this is the an example of image sequence in the UV filter. These images have been acquired in the first 3 slots, quindi 5, 12, so not the first 3, 5, 12 and 19 November. So there is 1 week between the 3 images. And this is purely UV filter. So you can see how the combination of changes inside the intrinsic changes of inside the plasma tails and the change of the view of the geometrical combination are indicating what's happening in the let's say gas and plasma environment of the comet. I have to say that one of the points that we are working on in these days and weeks is to investigate what happened to the sun, if something happened to the sun in the days just before this observation, in order to see if we can trace this irregular or somehow strange sun activity, considering the changes that we are observing in the ion and plasma tail. It is a very work in progress as a start. We started just in these weeks to explore this field. So, to conclude what's going on, and I invite you to stay tuned for a paper that we hope we will finish and prepare in the next weeks, let's hope, because we are working on the images obtained in the panchromatic filter for this first step. We are trying to investigate the structures inside the coma and the tails with a number of standard image processing technique, like for example the stacking of images to enhance the faintest structures, and we will see in a moment what we are working on. The application of enhancement techniques to reveal finer scale coma structures, filamentary features, jets, fans, and so on. Then this work will be analyzed in a 3D perspective, image by image, and the evolution of the coma will be analyzed. This is, for example, what we get when we combine all the panchromatic images that we obtained in the first slot with all the exposure time that has been used, from 1 second to 112 seconds. Each image in this case has been visualized and stretched in order to enhance the faintest structures that are present inside. So you can see how the general aspects of the tails, the dust tail and the plasma and ion tails, are very complicated to reconstruct. On the right side, you have the 3D panel of the relative position of the vectors. I also superimpose here the direction. You can see the sun is on our back. We are looking at the comet, and the comet moves along the trails of the star. This is what we got in November the 5th, and this is what we got the day after. So with only 24 hours of differences, the aspect is changed, and the combination of the change of the view of the site and of the geometrical relative position may be summed up with the variation, intrinsic variation in the plasma tail. And 1 week later, on November the 12th, this is the aspect of the coma that we got. So, this is the last one. Oh, no, okay, yes, okay. This is another step that we are working on in these days. As I said, we are trying to work on the images with several processing techniques. And in this case, we show here an example of this kind of analysis. On the left panel is the original row, not row in the sense, the original untouched image in the panchromatic filter. In the middle panel, there is the result of one of this technique. This is azimuth median normalization, and it is a structure that enhances the structures that underlie the symmetric distribution and is able to enhance jets and structures like tails, jets, filaments, and so on. On the right, there is the application of another technique. This is the modified Larson-Sekanina filter that enhances the presence of fans and jet-like structures, and this should be coupled with the relative position of the comet with respect to the line of sight and with respect to the sun. So we share with you some of the ongoing work that we are performing on this data, and stay tuned for a paper that we plan to submit, at least publish, hopefully, in the next weeks. And also we plan to present more evolved work on this subject at the next conference, SEM and APSC in September. And with this, I stop the sharing and thank you for your attention.
Thank you so much, Elena. Tobias is part of the ESOC flight dynamics team for JUICE. He was responsible for the precise targeting of 3I. He now leads the analysis team of the NAVCAM images for investigating 3I orbital dynamics. And it gives me great pleasure to hand over to you, Tobias, whenever you're ready.
Yes. Hi. Thanks for the nice introduction. So yeah, I put together the slides. So as you mentioned in my main occupancy, I'm working for the navigation team of JUICE and also other missions at ESOC in Darmstadt to make sure that, for example, JUICE goes to the target and really maneuvered spacecraft. But yeah, in this occasion, we were focusing on the JUICE images that were obtained and also the campaign to make these observations done. So we'll present a bit on this, how this worked, the challenges that were overcome, a few were already mentioned, and then what we get out of our own camera, basically our navigation camera on top of JUICE that we use then later on for the navigation in the Jupiter system, basically for operational reasons. So also maybe let me start with one quote. I was interviewed recently about the work at ESA, and I was giving some quote on a meeting, something like this year, cooperating in a multidisciplinary team may lead you to inspiring ideas and opportunities that you would have never anticipated before. And exactly when I was saying this a few weeks ago, I was having this campaign in my mind. So nobody anticipated this actually beforehand. So it was really inspiring what we got out of this. Let me hope I can present to you all how we did this. But maybe let's start a bit broader term motivation from a different point of view. Why do we do these kinds of observations? As mentioned, this was quite tricky from a orbital geometry point of view. I point here a few other examples. Observations of comets and asteroids and from spacecraft is by now nothing new, evolved over time. There was some nice observations from SOHO spacecraft that were only able because the spacecraft was able to point really towards the sun because of its imager. These kinds of observations you cannot do from Earth, from ground, because you would need to point your telescope towards the sun, and these low elongation observations are not possible because of the atmosphere distracting. Also, you can do enormous deep targets, like for example, observations done by James Webb only not too long ago of the asteroid 2024 YR4, which was potentially hazardous because it's had a impact probability with Earth, and being 50 meters, it could be quite a danger to Earth. And thanks to observations from spacecraft, we were able to exclude this percentage, basically completely now, which was nice to see. And spacecraft are quite helpful in this domain because they help because of their instruments and their orbital geometry to get to targets that we usually cannot see from Earth. And this is exactly what happened, as already mentioned before, for 3I Atlas, basically on its perihelion approach. It was basically on the other side of the solar system with respect to Earth. luckily, we had our spacecrafts there. We illustrating this nice page that was put together here. The path in the solar system, it was going to a close approach towards Mars, actually, or 0.2 astronomical units, or roughly 30 million kilometers, so comparatively close to Mars. And actually, we at ESA started also an observation campaign, as we did for JUICE, for the ExoMars TGO orbiter. We were also, our group was already involved in the analysis of this and published some results out of this. It was coming, the comet was coming to Mars, via Atlas was coming to Mars at a 0.2 astronomical unit distance. And we also investigated the images there to extract the source where it's basically in space, this comet, from the images, to precisely pinpoint where it is. And it actually turned out that we can really improve the orbital accuracy or dynamics estimation of this comet by this data. Basically, this kind of a stacked images of this all. Basically, what you get out of this is the position as seen from the spacecraft, where it is in space with respect to the background stars. So you kind of extract the sources and also the stars around, which you know where they are, and then you extract the exact position of the comet core. And with this, you can then, people do this, amateurs, professionals, big telescopes on Earth, and also now spacecrafts do this, and this can really improve the orbital knowledge of asteroids and comets, and leads us to basically getting to know where these objects are and if they are maybe potentially hazardous. In this case, okay, it was far away from Earth, so nothing urgent, nothing to do. But this is basically what our experts are doing at ESA to refine the orbits. Then later on, this was beginning of October, going towards the end of October, we reached the perihelion passage towards the sun at roughly 1.36 astronomical units towards the sun. And around this time, we also started with the JUICE operations and continued for quite a bit for the nearly full month of November, and observed that basically, distance quite grew after this over the time. So this is where you see this difference in the aspect angle as well. To target this object, there was a lot of things to consider operationally. Just to name a few, was already mentioned by Claire also in the beginning. We were just coming out of the very hot cruise phase of JUICE, which we say it's everything below 0.9 astronomical units towards the sun. As you know, JUICE is meant to go to Jupiter. Being in this really hot phase, you need to kind of have a lot of constraints. Basically, for example, as mentioned, put the high gain antenna. We use it basically as a heat shield and point this always to the sun. It was basically also not deployed overall. So we had also the problem of really low downlink data budget for our science data. Also, we were on the other side of the solar system, so the bandwidth is already by this quite limited. So overall, this made it only possible that we could only downlink the data recently. And also battery charging you need to take care of. You cannot off point too long to make these observations for hours and hours. So we had to really come up with a compromise in this. And also, there were also a bit of risks. I mean, there are some parts to be activated, some mechanical parts. So you need to evaluate this to kind of get to good compromise. But on the other hand, there was a lot to gain, and we already saw some results. Our nice instruments on board that have good equipment. Even though they're designed for Jovian moons exploration, they can also do some science with some tweaks of this cometary object. We had some campaigns going on also from NASA side. So and from us, the orbital knowledge of the comet, we could really nicely constrain, because first we are really close to the object, or comparatively close to the object with 0.4 astronomical units. And we look at it from an aspect angle where we are basically blind. Basically, if you watch from Earth, you can only see the up and right component, so to say, and from the object, we are basically from a side. So you could kind of get a, so to say, parallax effect, which can really help your orbital knowledge in three-dimensional space. So, and overall, also, it was a really nice exercise for the instruments already to see if everything is working fine. So yeah, when we were starting to plan this, so the comet was discovered, as mentioned before, in July 2025, and not short after we already started this campaign, and but the orbit uncertainty was quite high at this time already. So this was one of our initial plannings where we started. This is basically the position in space in a radial long track cross track frame. And yeah, we had a really huge uncertainty in the long track component, so up to 2 million kilometers, more than 2 million kilometers in the first iteration. If you take this is our navigation camera, so basically a really wide field of view camera. If you take this into consideration, so 1 pixel at this closest approach corresponds to roughly 4,000 kilometers of resolution. With this 1,000 by 1,000 pixels, roughly, you get a field of view of 4 million kilometers. So it would have been in the field of view of the navigation camera, but as mentioned, this is really far field of view. It could have been actually even out of the field of view from, for example, the JANUS camera or this smaller spectrometers. So this was quite critical that we have a good knowledge of the position of the objects already for the planning time, and then we iterated on and on with our colleagues also in Italy, our Near Earth Object Coordination Center at ESA, part of the Planetary Defense Office, to get a better hold of the position of the object. Yeah, and we designed this 6 slots and an additional one at the end where we basically are at the orthogonal angle with respect to the sun. We call this quadrature, where you can basically, we had to point our sun or antenna towards the sun, and our instruments were on a orthogonal side to this. So basically, you can just roll around the axis where we need to be by design for this medium hot cruise phase, and take long time exposures of the object. So and we luckily got nice results out of this. We iterated through and through and made a final planning for prediction together with our colleagues at ESA's NEOCC office. And in the end, had a really nice pointing. These are the images on the left, which we obtained from the navigation camera. So really far field of view, but already you can still see a bit if you modify the settings, the details in there. Also similarly changing or quickly changing over time from day to day. At the end one, we're quite far away already. You see also how faint the comet gets then with respect to the background stars. It was overall already quite a success from a navigation point of view of targeting the object. But we took it further. We wanted to know exactly how much we were off, basically, from our prediction. And that's where we analyzed our data. We had a lot of different also settings of the exposure times and tried to get a best hold of it. And and we tried to obtain the astrometry, so the position of the object in space, pretty precisely. We did this with the so-called comet method or zero aperture extrapolation. Kind of, if you start with a aperture of your image of the object, if you have a really large aperture, because the comet is not a spheroid or a sphere basically in the image. So depending on which aperture size you use to get a centroid, it changes because we don't know how the orientation is perfectly of the coma and the and if you go from a big aperture towards a smaller one, you get kind of closer towards the core of the intensity of the light peak. This is what we are interested in. Where is the central core, more or less, of this? And if you go closer and closer, you get towards the and we kind of did an extrapolation of this, and always put the reference stars. There are a lot of stars you can see in the background of these images, which are from the Gaia catalog, which is a really precise measurement of where the stars are in the background, so you can get a really good hold of where your object is with respect to the stars. And we got really nice quality out of these images, nice SNRs. And here I put this together, a small animation of all the images. You can see it a bit flickering because of the different exposure times we selected for the images. So you can see how it's moving and changing details. I didn't do much around the images, no reorientation, just draw how they got out of the spacecraft. Already quite nice to see. And what we were interested in now is the exact position with respect in the solar system. And it already showed in first preliminary results that there's really some high astrometric value of these images because we are so close to the object and also looking from a different angle. So it really can constrain our orbital solution quite drastically, especially because what was a bit of the unknown parameter, or still is a bit, is that as the comet is outgassing, the mass distribution of the comet is changing over time, and also gives kind of an impulse. So the movement of the comet is slightly changing, or the trajectory is slightly changing compared to a simple Keplerian orbit. We're trying to get a hold of this based on the material that is outgassing and also the amount over time, how it changed. This trajectory can quite change a bit. So we're trying to model this with non-gravitational models based on the observations we have from our spacecrafts and together with the ground-based data. And our initial results showed kind of a discrepancy between the spacecraft observations we obtained from TGO and JUICE with respect to the ground-based data. So this was quite interesting to see. We were getting a bit of hold of this, and we are still working on this more precisely to really estimate how much of material is outgassing, how much is changing the orbit of this, as this is really valuable data for this. But this is a bit of effort because we have to kind of get a hold of kind of all super precise things that need to be taken care of this in these images. For example, any time offset of milliseconds. Also, the position of the spacecraft itself needs to be really precisely known. This is why within our teams in flight dynamics we try to really estimate the position of JUICE as precise as possible, which we do on a routine basis anyways. To get good understanding that we introduce any systematic bias that could interfere with the results in the end. So just why we're taking our time to really understand this, because it's not too long ago. So it's kind of really first times this is done. So doing these astrometric observations from basically the other side of the solar system. Usually this is only done from Earth or spacecraft around Earth orbit, but really from a different side of the solar system. It's kind of a novelty. So this was not really done for these kinds of purposes. This is why we double check everything before really going further with this. It was a really good success. We have a lot of lessons learned, and overall the images shown really good pointing performance, and as also shown by our previous speaker, already great scientific results. Here's, for example, a comparison we did. We were also even always cross-checking our results of our offset of the prediction that we had with respect to where the actual observations were then afterwards of different sources. So we were also cooperating with our colleagues at JPL, checking where their predictions were of the object, because as said, this was quite uncertain at the beginning. In the end, it turned out we went for this final planning that this was done, just blue dots. Actually, these were already quite good. On the other hand, if we would have trusted the source that we obtained from our JPL colleagues in the US, this would have been quite off already. So it was a good decision to get a hold really precisely of this in advance, because this was several arc minutes off actually. So this could have been really even already out of the field of view of some of the cameras and spectrometers. So we wouldn't have gotten these nice scientific results if we went for this in the end. So this is good to see. So and also we saw spacecraft is really providing powerful astrometry results if you do this, and which is extremely valuable for precise asteroid and comet orbit characterization, because we're so close. And really high potential for also potential other candidate or targets. And but alongside also our teams, we learned also a lot. We had a lot of technical discussions, because this was kind of a first in many domains. Discussions about reference system, because this would really introduce a lot of biases in your data if you don't take this into account properly. And we learned basically on all sides a lot of useful things, or to make this precise spacecraft operations really possible. And but maybe also to highlight, it was really nice cross-department work. There were so many people involved in this. So our whole teams in the Science Operations Center, or teams here in the Mission Operations Center in Darmstadt, and also our colleagues in Esrin providing us the orbit of this interstellar comet. So it was overall also immense team success to make these things happen. So maybe let's close with this for my presentation. There's a lot more to come up. We are having still the hold of this complex outgassing models to really assess the dynamics of the comet really precisely with the data we have, also from the other cameras potentially. Also with the data from ground now after the perihelion passage, eventually publishing also the data resolved, and then let's see what we also find for other targets. So because this turned out to be really useful, and overall really like this joint work of all the teams connecting them. Thanks. Maybe stop with this. So thank you for listening.
Thank you, Tobias. I encourage everybody now to ask their questions in the Q&A. Thank you, Elena, for being so active in the chat and answering so many of the questions for your presentation already. I'd encourage, if you were one of the 5 people who asked a question for Elena using the Q&A tab, have a look in the Q&A tab, because you will find them answered in the answers tab at the top of that box when you open it. We're a little bit past the hour now, but since we've got so many interesting questions and we had so much content to get through, we're going to hang on to our speakers for a little bit longer and get through some of our questions and start a conversation. So if we can start with Marshall. Marshall asks Tobias, did you use zero aperture with the TGO data?
Yes, so this method that I was just presenting about, you go closer and closer to with the aperture of your analysis, basically. This we also did for the TGO observations that we already published. Yeah, it's be done.
Thank you. Our next question is from Luigi, who says, hello, Tobias. Very nice work. Could you tell a bit more about the magnitude of the difference you see when you compare ground versus space observations?
This we didn't have get a hold really now. So the photometry, this would be interesting. Good point, Luigi. Thanks to mention this. But of course, the object appears to be way brighter than as seen from Earth, because we are closer to it. So the apparent magnitude is, of course, higher than that. For example, for the observations we were doing from TGO, we were going to 11 magnitudes, I think. So comparatively bright. but yeah, I have to double check for Juice. I don't have the numbers with me currently.
Mm-hmm. Thank you. Okay, we have just one more question in the Q&A, and I don't see any in the chat. So if you have a burning question, now is your chance. Our final question for now comes from Nicholas, who says, question for Tobias. Were the predictions for the imaging done taking into account non-gravitational forces with standard Marsden type models? And was the limiting factor of the NGA models, sorry, let me try that again. And was the limiting factor the NGA models or the astrometric uncertainty? Thanks.
Yeah, so we didn't do for the predictions of the pointings of the imaging. We didn't take this in account yet because we already had the sparse or smallest data set of a few months of the orbit beforehand, and there we couldn't really estimate any gravitational forces because they only play a role really towards the closer solar system, so they only become observable really there. So this was not done yet. Yeah. So, and the last part of your question about the models and the astrometric uncertainty. So these observations really turn out to be quite accurate. It was a positive surprise to see. So this led us to the decision that we actually that the standard models that are used currently that are lacking of kind of these effects. So we are kind of sensitive to even distinguish around this. So this we are investigating now.
Wonderful. Thank you so much. We seem to have reached the end of our questions, which is great. Thank you to everybody. Oh, I'm sorry. We have had one more come through, and we'll answer that in just a moment. Thanks, everybody, for asking your questions using the Q&A. We do have one more from Thomas, who asks, Elena, have you already tried to model changes in dust/gas ratio over time? Elena, what do you...
Yes. Do you mean, Thomas, with the JANUS dataset? If this is the case, the answer is no. We do not have tried already, but our plans is to at least see how the general behavior of the brightness changes in time. We have 20 days of time covers and see if the changes in the coma, considering the filters, the adopted filters, can be used to trace the evolution of dust to gas ratio. But in any case, these are they are not large band filters, but they are not narrow band in order to check molecular emission. So we have to take also this into account, even when considering, for example, the ultraviolet filter and so on.
Wonderful. Thank you so much. Okay, we are at the end of our session. Thanks everybody for hanging on for an extra few minutes over the hour. I hope you'll all agree that was a good thing for us to do. Thank you, all of you, for coming on and giving up your afternoon to join us for this session. Thank you to all of our speakers, to Claire, to Elena, and to Tobias. Thank you to Olivier and to Martin for helping to organize the session. We'll be back with another JUICE webinar in just a couple of months' time. We'll be back with another Europlanet webinar next month. It's great to see so many new people. Hope to see you again. See you all soon.
Thank you. Bye to everybody.
Thanks. Bye-bye.
Bye.
Bye, everyone.